Hey, welcome to the course on algorithms and techniques for autonomous driving. This is Zhonghua Gu. I am the instructor for this course, as well as Kala Prarak, who is also shown on Zoom. So first of all, the logistics. The lecture times are Monday and Wednesdays, 14 to 16. Here's the Zoom link, which is in Canvas. So please bookmark this page. So here's the instruction style. I have no textbook. I will discuss classic techniques as well as latest research advances. Therefore, I cannot find a suitable textbook. Textbook materials are too old. So I will provide detailed self-contained PowerPoint slides. They are the full content of the course. So all exam questions will come from these slides. Some slides may be verbose for the sake of completeness, because I don't have any other document or text for the lecture material. In-class questions and discussions are always welcome. You can either just speak up during the lectures, or you can type in the chat window. So I'll try to answer interesting questions during class. For questions after class, please use the Canvas discussion board so everyone can see the discussions. Lecture videos are recorded and available on UMU Play. So in-class attendance is not mandatory. So here's the tentative lecture schedule. The first lecture will be introduction and overview of various aspects of the autonomous driving field. Week 2, I will discuss functional safety and ISO 26262 for safety certification in the automotive industry. Notice that there's no class on April 5th due to Easter holiday. Week 3 will be on perception. I will provide introduction to machine learning and deep learning, as well as convolutional neural networks. So this part was not in last year's course, but I feel that it's important, and I added this part this year. Week 4 will be planning. I will discuss so-called classic planning algorithms, including high-level route planning and low-level trajectory planning. Week 5 will be control. I will discuss the commonly used control algorithms such as PID and MPC. Weeks 6 to 7 will be on reinforcement learning and deep reinforcement learning. Weeks 8 to 9 will discuss other applications in autonomous driving. Weeks 10 to 11, I will discuss more advanced research topics, such as security attacks and defenses, uncertainty estimation, auto distribution detection. The topics may be subject to change depending on my update of the my collection of the research material. For example, the uncertainty estimation is when you decide that a perception or control decision is unreliable because the deep learning model is uncertain. So know when you don't know, and then you should make a appropriate response. For example, to transfer to the human driver or perform some emergency maneuvers when the machine learning model is uncertain. So out of distribution detection is when the vision input is not in the training set distribution. So it's therefore the decision, the prediction from the neural network model cannot be trusted. So I may collect other topics. So the topics in the last few weeks will be pretty much open right now. So I will put lecture materials here on the GitHub IO link instead of on Canvas. The main reason is that during the lectures, I may find some minor issues with the slides, so I may update the slides after each lecture. So it's much easier to do this on GitHub. Also make sure that you download the latest slides 1 day or 2 days after the lectures. So here's the website. Right now it's pretty much empty, but I have the first lecture online. So you can download this while I am giving the lecture. It's my name, Gu Zhonghua at github.io/SAAV. So for the lab sections, I will give out lab 1 in week 3 to 4. It'll be a traffic sign classification project with convolutional neural networks. Weeks 5 to 6, I will give a lab on adversarial attacks on CNN classifier. For example, you may add some minor perturbations to cause the classifier to misclassify a traffic sign as a speed limit sign or some other object. Weeks 7 to 8 will be a project on control. You will implement a simple PID control algorithm in the simulator. Weeks 4 to 5 will be reinforcement learning as applied to autonomous driving. So Carla Prorok, the other instructor, will provide brief tutorials on related software frameworks such as TensorFlow, Google Colab, IR frameworks, etc. Throughout the term as I give out the assignments, the labs. So the grade distribution is 60% for the final exam, which is open book, open note. You can take it on your computer. You can look at all the PowerPoint slides or anything you can find online. The lab sections are 40 points, 40%. So in terms of the projects, so we'll try to keep the project's computing demands low. So you can use Google Colab online or work on your own computer without powerful GPUs. So many of the deep learning models take a very long time to train and require large GPUs. I think that's maybe not realistic for many students. So I'll try to make the programs involved relatively toy-sized examples so that you can train the models within a few hours or at most a few days. So the programming workload will be kept relatively low. For example, you may be given a semi-complete program and asked to tune some hyperparameters or fill in a few lines of missing code. You won't be asked to develop large blocks of program, large amounts of code, so that each lab assignment should be finished within 2 weeks, and in terms of hours should be within less than 5-10 hours. So programming language is Python. So at this point, Carla, do you want to discuss a little bit about the labs?
Absolutely. I can mention a little bit short about the labs. Do you see me? I don't see you. I can maybe share my screen. So we have, I'll just share everything so you can see my mess. We are going to talk about, sorry, move this stuff. Do you see my little Acrobat stuff? Hello, anyone?
Yes, we can see it.
Yes,
yeah.
we can see.
Yes. So we are going to look at deep reinforcement learning, and it's about an agent who takes action and do something and got yeah, I'll just move a little bit quickly here. So you have a software agent that takes an action which changes an environment, and you get a new state and you get reward. That is it a good state or bad state, and so on. And then you try to learn the best action to take when you are in a certain state. So how to maximize your happiness or something like that. So we have a lot of stuff about these things. And then the labs, we will, for the deep reinforcement learning, we will use, see if I have this. I was a little bit surprised. We are going to use, oh, I can restart it here. It's something we call highway environment, where we will see how a car could drive and learn to drive and merge and roundabouts and maybe parking and intersection and so on. So we try to make our computers learn these kind of things. But then it's needed to have powerful computers. So instead we will run this in Google Colab, which is, yeah, you can open here, maybe trajectory planning. So here you see it starts in Colab Research Google.com, and then you have a web page where you can run your code without any need to buy expensive hardware. So here instead you can go to select machine, accelerator, GPU, for instance, save. So here you can run in 10 minutes or something instead of maybe several hours on your normal PC, unless you already have an NVIDIA board like 1070 or better, then you can run on your own computer, and then you might run for longer time overnight and so on. So this is about the labs. So we haven't done them yet. There are many weeks remaining before these labs. So we see what's happening, but we will mainly go for this highway solution, how to make things. Last year we have something car racing and mountain car and so on, but they are a little bit demanding. It takes a lot of, like, several days of running, so we don't plan to use them this year. So there will be some changes, and that's the reason we are not ready by them yet. So
Yeah, so if you have difficulties working with Colab or Python in general, Carla is an expert on these topics, so you're welcome to post questions on Canvas.
Yeah, if you're not used to Python, it's good to have maybe a quick course if you're used to other programming languages and so on. Absolutely. There was a question?
Yeah. Is there any resource center in the university where you can submit instead of Google Colab? Because Colab is still limited to resources, right?
So Colab is just a web page. Yeah.
Did you mean they offer? I mean,
is there any? Yeah. Is there any lab or cloud infrastructure in the Umeå University where you can submit our like Python job that has some GPUs to run? With the large data, Colab also is not really working. Maybe in our labs it may.
Yeah. We have computers, but I don't know. We don't have any lab computers, as far as I know, with GPUs.
Colab is free for everyone, except if you're a free user, you don't pay anything, then there's some minor issues. For example, it may time out after a few hours. Yeah, but there are ways to get around it. You may have some kind of script to prevent Colab from timing out. In general, I don't see any issues with using Colab. Do you see any problem with Colab?
Seoul mentioned something. I think
no. I mean, I was just wondering if the data set is too large, then Colab doesn't work too, because it still has a limitation. But I think for our course, it's going to be fine.
Yeah, of course, if you're making very big models and so on. But actually, Colab is very recently they increased the powerfulness and the disk space and so on. So most problems where you can run on your ordinary, like normal 10,000 crown GPU board, it's possible to run in Colab as well. So, but then there is Kaggle and there's Azure and there are other places as well, which we can try if Colab happens to not work. So,
okay.
So I ordered I have a 2080 Ti card and wish to buy a 1390 board from NVIDIA, but they are like 1 year delivery time or something. So it's very slow to get them and expensive.
Yeah. One more question. Can we use a pre-trained CNN networks for the classification tasks there?
The lab one, I think I'll perhaps give you a deep learning model with randomly initialized weights, and you can tune the hyperparameters. So that's the current plan. So lab 2, you can the adversarial attacks are starting from a pre-trained network. So you can either use your classifier from lab 1, or you may use a pre-trained one you find online. I think that's fine. For labs 4 to 5, it's not finalized yet, but the highway environment for autonomous driving is fully open source, and they provide some baseline agents. So you have a pretty good baseline to start from to train your agent.
Okay, thank you very much.
I got a question also about a book about Python. There are many books and there is also some online resources. So I will have a look and put it in Canvas tomorrow so we can make a smarter decision that I can decide today.
If you're new to Python, maybe Carla can collect some useful links to be posted online. Or you can give a maybe 1 hour tutorial sometime on Python and TensorFlow and Keras.
Very good comment. Thank you, Songa. Yes, we had this course last year. And as a teacher, you know, we don't have very many hours. But I was thinking if we kind of reuse last year's recordings, then I will have some free time, and then I can teach you Python, and I can teach you more in detail about Keras and so on. So then we can spend the time with more practical hands-on and questions and more interactive stuff. And then you need to study the videos or recordings on yourself in advance. I think we call it flipped classroom. And I think it's a very effective way of learning, because then you can just study the easy things on the slides and listening to the recordings, and then we can have an hour or two with discussion instead. I think that's more fun for all of us, but I don't know. We haven't decided yet. So any comments are welcome.
Yeah, so last year, Carla recorded some videos on reinforcement learning using the RL frameworks. So these videos can definitely be reused. So I put them on Umeå Play sometime later.
Yeah, I have them on Umeå Play. I can put them there, so no problem. So I can put the links in a new section in Canvas tomorrow.
But is it only available for students who registered for last year's course, or is it available to anyone who can log in?
I will put them so anyone who can log in our course, of course. Yeah. And there's a question about PyTorch also. We had a discussion about PyTorch, which is, you can say, competitor to Keras and TensorFlow. And PyTorch is more popular, and it's also even better for reinforcement learning, but it's a bit more complicated. So we decided to go for Keras, but as far as I can see, you can use PyTorch, and I will mention PyTorch as well on some of the lessons, because it's more like, if you deal with interactive learning, PyTorch can be even simpler to use than Keras and TensorFlow. So I don't know about Songa if we accept people using PyTorch or not, but what do you think?
So frameworks don't really matter. So as long as the fundamental technique is correct. So I think the first two assignments will be, it's not entirely finalized, so it could be based on PyTorch. But really, PyTorch and TensorFlow are getting more and more alike. They used to be different, but recently they are becoming kind of borrowing from each other. So I think it's really not difficult to learn either framework.
No. And then we got a question about R. I know R, but I think R is not really possible to run here. I'm not sure about that, but at least our examples and so on are written in Python. So I think R will be difficult to use.
Yeah, I never used R, so I don't know anything about it.
The statisticians are using R a lot. Pydroid, I don't know what Pydroid is. Sorry to say. Pydroid.
I'm having trouble seeing the chat. When I click on chat, nothing happens.
Yeah, Alt H. Yeah.
Yeah, let me try. Nothing happens.
You have two windows, you know, so
Oh, here.
So I have to look at the other Zoom window. And Fast AI, yes, we're going to look at Fast AI, but PyDroid, I will have a, need to have a look at PyDroid app. Okay.
Haven't
So
heard
it's
of
for,
PyDroid.
okay. So it's to running Python on Android devices. Can work, I'm not sure. And there is a TensorFlow Lite to be able to run on Android devices as well. So I will have a look. That's an interesting thing, but we can't answer immediately. Yeah.
Well, I think it's more of an educational toy. I mean, why would you develop programs on Android?
Yeah. Complete stick winter terminal, OpenCV and cameras. Yeah, we have to have a look, but you mentioned TensorFlow is mentioned there in PyDroid. TensorFlow and PyTorch are also available. So yeah, I guess the device is too weak for our labs. So they might run for 10 minutes on a Colab, but it certainly will take many hours on a mobile device.
So Fast AI, someone mentioned Fast AI. It's a very good set of tutorials for deep learning. So if you have zero knowledge in machine learning or deep learning, it's definitely a good resource to get up to speed. I will discuss the key concepts useful for the course, so that you should be able to follow the course without any additional tutorials. So for example, I will discuss machine learning, the basics, before I introduce convolutional neural networks. But I think Fast AI is useful, especially I think they have some very good hands-on materials. Yeah.
Yeah, there are millions of very good deep learning toolboxes and so on. And I'm working, I will fetch the book by the way. Yeah, so I have like this, for instance, deep reinforcement learning in action. So there's a company called Manning who has online books quite cheaply. And here's my Python 3 book, but it's a little bit old now. So Python is in new versions. So it might be important to have a recent book. But there's a lot of deep learning books as well. Deep Learning Illustrated is a very nice book and so on. So there are very many books. And I'm working now on the Keras book by a French author. He was supposed to be ready last year, but he only have written half the book yet. so I don't know if it will be ready tomorrow or next year. So that's a problem. But if you buy the new book, you have the old book included, so you can read in the old book meanwhile. But then, yes, this we have Geron as well in machine learning. So I will fetch that Geron book as well. So this Geron book is maybe the best because it includes TensorFlow 2. So if you have the new version, then you can. And then you have a basic about machine learning as well, about traditional machine learning. So now we were looking at deep learning and deep reinforcement learning, but this Geron book also contains a lot about traditional, like, yeah, many other ways of doing AI.
So, Carla, could you put the relevant links on Canvas after the lecture?
Absolutely, yeah. And some Python links as well. So we'll try to see if there's some updated version. Of course, you have the Python homepage where there is a course, online course we can follow. That's maybe the easiest, cheapest, and most modern.
Okay, so I see Maximilian has a question that what do you mean with open book? By open book, I mean that the lecture, the exam is completely open. So you can look into the PowerPoint files and search online or do anything during the exam. So it will not be monitored. You just need to, I gave out the exam paper at a given certain time, and 2 hours later you turn it in. So, and you can pretty much use any material you can find to answer the questions. So that's what I mean by open book. So because it's a remote online course, it's really not possible to proctor the exams. I think the main purpose of the course, is to teach you knowledge, to let you learn knowledge, not to try to give you a hard time. So the important thing is that you learn something new from the course. As far as the final grades are concerned, I don't intend to fail anyone. I don't expect anyone to fail if you turn in your assignments on time. Okay, any more questions on the course logistics? Will you given previous exams as well for preparation? Yes, I will give you maybe sample questions from previous exams from last year. This course was initially offered last year, so it's the second time I'm offering the course. So I don't have too much experience with the course. And the previous exam, I may reuse a few questions, but I can give away some questions to help you prepare. Generally, it's multiple choice or short answers or fill in the blanks, etc. Okay, yeah.
I was a little bit curious about the language. We're running in English. At least myself, I can answer questions in Swedish. So if you find it difficult to formulate yourself in English, you can send Swedish questions to me. And I think Songo also soon to know a lot of Swedish. But I don't know. I guess we have students on the course who doesn't know Swedish. Please ask your questions in the forums and so on in English so everyone can understand.
Yeah, I wouldn't expect that to be a problem. I think especially if you are a college student or engineer, you should be pretty good at English. I'm also learning Swedish myself, so if you ask in Swedish, I can try to answer.
So if there is no more questions about the labs and so on. I would say for myself that this is the most fun course of all my courses. This deep reinforcement learning is really fascinating, how the computers can learn itself to do really advanced things. And for autonomous vehicles is almost the only solution, because we cannot pre-program the vehicle to deal with a lot of situations. So the best is to make the vehicle learn by itself in some way or another. So I think this is really the future, not only for vehicles, but also for many other things. So for instance, for proteins and so on, they found that this deep reinforcement learning is working very well for making good medicine in the future and so on.
Yeah, I have this, my YouTube channel has lectures from last year. So you can watch it for reference, but there will be a lot of updated material this year. So including perception part, and for the reinforcement IR reinforcement learning part, the content will also be updated with more recent research, and also some additional topics such as security was not covered. So and also uncertainty estimation, etc. So there will be a lot of new material.
Yeah, someone asked if you can comment about the changes from the last year. I don't know. I will look through my videos, I think, or I should, and then based on that, during the kind of interactive session afterwards, we can discuss more things based on what was recorded. So I will see them myself as well. So, but we got a question about industrial partners, and myself, I'm working with Trafikverket. So we have a lot of projects, but my friends at Algorix here in Umeå made a deep reinforcement learning algorithm which they presented yesterday. So it was based on Unity and their toolbox for physics, and they are selling to many hundred industrial partners in the world. So many very big companies are using this Umeå company software. So I will put a link also in the discussion forum if you are curious, because it's hot topic, so to say. It's yesterday's deep reinforcement learning results.
So maybe you can ask their engineer to give a guest lecture sometime later in the semester.
Yeah, could be. And they have many videos also, so you can already look at them if you want to have some ideas. But I can ask if they want to have a guest lecture. That could be good. So, yeah. So I will ask them, and then maybe if you're doing your master thesis or so after this course, then maybe you do it with them in some way or another.
Yeah, we don't have any official industry partners in the course, so it's mainly a university course.
I see Rui is going to ask you in Chinese.
Yeah, of course. I'm Chinese, so if you know Chinese, you can ask in Chinese.
Isn't there many versions of Chinese? So Mandarin and...
Yeah, many dialects, but Mandarin is the standard Chinese.
So I'm asking because I'm working now with research project for language learning, and that's the next step maybe after reinforcement learning is they start to speak. And yesterday they presented at Kungliga biblioteket in Stockholm a model that learns from talk to text, from speech to text in Swedish. This is the first one as far as I know. And within 2 weeks, there will be a question answering system with deep learning. And then you can ask questions for someone's exam, and then you use this AI method and then you can get an answer. Maybe we'll make a robot that makes the exam. Oh, sorry, Songa.
Yeah, sure. Let me emphasize that this is not an AI course. I mean, AI is indispensable in autonomous driving, but traditional techniques such as traditional planning and control are also very important. So especially for industry deployment, most companies are still relying on the traditional methods. The learning-based methods are gaining more and more ground, but you know, they are not as mature as the classic techniques.
Yeah, and we will keep track on Tesla. I read yesterday they have a new version which is more autonomous than yesterday's version. But I don't know how advanced it is, but it's really very exciting. So it will happen a lot of new things during the course as well. So including safety issues, of course. No more questions?
Okay, so let's take a 10-minute break before we continue. So we'll resume at 2:55.
So we will get a wake-up call if you fall asleep.
At least on my computer. Yeah, okay. See you in 10 minutes.
So yeah, and I will do this other stuff meanwhile. So if you have any questions, don't hesitate to send an email or write in the forums and so on. So good luck with the course now. Thank you.
Okay. Okay, I hope everyone is back. So I have another question from Yavir. He's asking if every lecture will be recorded. Yes, all the lectures will be recorded and available on Email Play. So if you go into Canvas and go to on the left of the menu, you can find Email Play. So I will upload the videos online. So this is last year's lecture, which is the same as the lectures on YouTube. So I'll upload the Zoom videos online onto Email Play after every class. So it should be up there after a few hours. Okay, so let's continue with the lecture material. So today's agenda is on the broad overview review of the major issues in autonomous driving, including the background, history, sensors and perception, high-definition maps, hardware and software platforms, and ethical issues, and V2X communication. So autonomous vehicle can refer to any type of autonomous mobile robot, not just self-driving cars. So it may be a car, maybe a drone or warehouse robot or indoor cleaning robot like a Zumba. So many techniques for self-driving cars as covered in this course are generally applicable to other types of AVs. So why autonomous driving? So the number one motivation is reduced traffic accidents and fatalities. In the USA, in 2019, estimated 38,000 people lost their lives to car crashes. About 4.4 million people were injured, seriously enough to require medical attention in crashes. So this is just data from one country. Worldwide, it's a serious, traffic safety is a serious issue. So hopefully AD will help alleviate and reduce traffic fatalities. Another is reduced congestion and pollution. So this may be a contentious point. You may argue that if all the vehicles are autonomous, people may take longer trips or use their vehicles more than manually driven vehicles. But it may also be possible to reduce congestion if the automation has a large penetration. So that the traffic is more efficient in general, and traffic jams are less common because of better planning and better driving. So for individual passengers, you may be more productive on the road. So you may get in an autonomous vehicle and do your work or take a nap or do anything before you get to work. So autonomous mobility on demand with a fleet of AVs. So this is the dream of companies like Uber and Lyft. So this is a low cost, safe, and efficient mode of transportation that may make vehicle ownership obsolete. So the number one cost of these companies like Uber is the drivers cost. So if they can get rid of the drivers and they own a large fleet of AVs, it's very profitable for these companies. So ADAS, Advanced Driver Assistance, is a very old technology. Since the initial introduction of cruise control in 1948, ADAS functions are increasingly prevalent in modern vehicles. There are many acronyms such as adaptive cruise control, anti-lock braking, collision avoidance, driver monitoring, electronic stability control. So ESC is, especially if you're driving on the icy road, ESC can help you control your brakes to avoid the skidding and turning over. For collision warning, this is useful for applying emergency brakes if it detects a imminent collision. Lane departure warning, this is when you're driving and your vehicle deviates from the current lane. Lane change assistance, it warns you if there's a vehicle backwards or when it's dangerous to change lanes. And surround view, that's when you have kind of bird's eye view of the surroundings of the vehicle collected by multiple cameras pointing in different directions. So in high-end vehicles, many of these ADAS functions are already available. So if you talk about autonomous driving, you must mention the Darpa Grand Challenges. These are competitions that really give birth to the entire autonomous driving industry. So Darpa is the Advanced Research Projects Agency, a Defense Advanced Research Projects Agency in the United States. So they sponsored 3 grand challenges on autonomous driving. The first one was in 2004. It was held in the Mojave Desert region along a 150-mile route. None of the robot vehicles finished the course. So Carnegie Mellon University's red team and the car called Sandstorm is converted Humvee, traveled the farthest distance, completing 11.78 kilometers of the course before getting hung up on a rock after making a switchback turn. So because no vehicles completed the whole course, no winner was declared, and the cash prize of $1 million was not given to anyone. In next year, 2005, things got better. So in this route, vehicles passed through 3 narrow tunnels and negotiated more than 100 sharp turns, left and right turns. There are 5 vehicles that successfully completed the 212 kilometer course. Stanford's Stanley vehicle won the $2 million top prize. So in 2007, there's a so-called urban challenge. So the previous 2 challenges were on a kind of non-urban environment, where this one you have to drive in a Air Force base with the traffic signs and other traffic around and so on. So you must obey all the traffic regulations while negotiating with other traffic and obstacles and merging into traffic. So it's more challenging than driving in the desert. In this race, CMU's boss vehicle won the 2 million top prize, and Stanford's junior won the 1 million second prize. So the table shows the top teams in the race. So the three grand challenges, the three races jump-started the self-driving car industry. Faculty and students from winning teams such as Stanford and CMU later became leaders in SDC projects at companies like Google, Waymo, and Uber, and numerous other startups. So highway driving is perceived as an easier problem than city driving. In terms of travel speed, highway driving is faster. Traffic volume, highway driving is higher. The number of lanes is larger. And the difficult point is entry and exit points for traffic merging. Whereas for city driving, speed is slower, volume is lower, lanes are smaller, and the main challenge is many intersections with the traffic lights. So highway driving has potential of massive displacement of truck driver jobs. So it's actually very realistic because highway driving is easier to automate. There are already automated trucks on the road, of course, with human operators on board. When you are entering and exiting the highway, a human operator needs to intervene. But during the driving, the human can pretty much go to sleep. It works pretty well. But traffic merging is still very tricky. So here's a very brief history of self-driving cars. So started from the 3 Darpa challenges in 2004 and 5 and 7. And then in 2009, Google started its autonomous vehicle project. And in 2012, Google's vehicle passed a 14-mile driving test in Nevada. And 2013, Mercedes and Infiniti produced cars with radar sensors and some AD features. 2013, the National Highway Transportation Safety Administration in the US releases initial policy on AVs. And 2015, Tesla releases autopilot. And 2015, Uber hires 40 CMU robotics researchers to work on AVs, and Ford begins testing its AVs. And 2016, major acquisitions and partnerships, GM and Cruise Automation, General Motors and Cruise Automation, GM and Lyft, Toyota and JBridge Robotics, Uber and Volvo, and so on. And 2016 and 17, NHTSA issues guidelines for testing and deployment of AVs and revised safety guidelines for AVs. So the operational design domain, ODD, defines the conditions under which a vehicle is designed to function and is expected to perform safely. The ODD includes, but not limited to, environmental, geographical, and time of day restrictions, as well as traffic or roadway characteristics. For example, an autonomous freight truck might be designed to transport cargo from a seaport to a distribution center 30 kilometers away via a specific route in daytime only. So this vehicle's ODD is limited to the prescribed route and time of day. It should not operate outside of it. So perhaps this particular route has a high definition map available, and the vehicle can travel this route very safely. But once it deviates from the route, it may venture into an area with no HD maps. Then it's outside of its OOD. Also, maybe weather and lighting conditions. For example, autonomous driving is generally much easier in sunny weather. So that's why most of the AD testing is done in dry and sunny weather locations such as California and Arizona. So if you test the vehicles in Canada or Sweden or Michigan, the conditions in the winter are much more difficult, especially if you have heavy snow. Then it pretty much disrupts all the vision functionality and makes the vehicle to go outside of its OODD. So it's important to specify the ODD of the autonomous vehicle. So the 5 levels of automation. Level 1, driver assistance. So that's the ADAS features that either control steering or speed to support the driver. So level 2, partial automation. So the both steering and acceleration are simultaneously handled by the AD system, but the human driver still monitors the environment and supervises the support functions. So in level 1 and 2, you are the driver, even when the automation features are turned on, and system supports you while driving. So, and then level 3, you notice that there's a large gap between levels 2 and 3. So level 3 is conditional automation. So the system can drive without the need for a human to monitor and respond. However, the system might ask a human to intervene, so the driver must be able to take over control at all times. So, so for level 4, it's high automation. So these systems have high automation and can fully drive themselves under certain conditions. That is within the ODD. So the vehicle won't drive if all conditions are not met. So I have a typo here, the unlimited ODD. So the last, the highest level is level 5, it's full automation. The vehicle can drive whenever, wherever with unlimited ODD. So most autonomous vehicles today operate at level 3 or lower, especially, for example, Tesla is level 3. So the a large gap between levels 2 and 3 means that it's a difference between ADAS and autonomous driving. So current commercial products are at most level 2. So Tesla sometimes say they're level 2.5. Sometimes they say it's level 3. But generally it's a level 2 or 3. So automakers keep pushing the timeline of level 3 and above to the future. So there are 2 different paths to level 4 and 5, highly autonomous driving. So in the figure on the horizontal axis is the scale. Let me see, scope of the vehicle. So from prototype closed course to fleet limited geography to mass deployment everywhere. So that's the ODD, operational design domain. On the vertical axis is the level of automation from 1 to 4. Level 5 is too far away, so level 4 is the highest people are aiming for. Tesla starts from ADAS and mass deployment and gradually moves to level 4 and 5. So they have a large fleet of vehicles on the road today. And every Tesla vehicle collects the video data and uploads all the data to the server in the cloud. And they train the AI algorithms based on the collected data. And hopefully, the autonomous driving features will gradually improve and gradually reach level 4 and 5. But Waymo and other companies, Nutonomy and a few others, start from L4, level 4, in limited geography, for example, in the city with high definition maps available, and gradually expands the deployment to try to make it be deployed on more in a mass scale. So their argument is that it's not realistic to expect the driver to take over control at any in a short amount of time. It's just too difficult. Humans have bad attention and humans are not reliable. So Tesla's approach of alerting the driver whenever there's any critical situation is not safe. So that's the argument of Waymo and others. So that's why they start from level 4, but in a very limited ODD, in a very limited region and limited weather condition and with other limitations, and gradually expand the ODD to be more broadly applicable. So these are the two different technical approaches for achieving the L4 driving, autonomous driving. So the AD safety evaluation metric, the most common metric is miles driven, but not all miles are equal. Driving conditions may be dramatically different. So companies may be incentivized to avoid difficult driving conditions to rack up the miles, so to say. So for example, miles driven at a difficult merging point to a highway versus miles driven on a country road with no vehicles. Obviously, the level of difficulty is different. So this is the total miles driven. In 2019, Waymo reaches 10 million miles. And in 2020, Tesla's autopilot reaches 1 billion miles. So Tesla has the 1 billion miles large mileage because it's the sum of all their fleet, all their vehicles in autopilot mode. So they have lots of vehicles already sold to consumers. So whenever the consumer turns on the autopilot feature, it's counted as part of the time. So that's why they have 1 billion miles in total. So this is miles driven per disengagement. So disengagement, as defined by the California Department of Motor Vehicles, is a deactivation of the autonomous mode when a failure of the autonomous technology is detected, or when the test driver disengages the autonomous mode. That is when the human must intervene. Either because the human feels unsafe, that's pretty subjective, or there is a failure of the AD function. So there's a lot of disagreement on the level of accuracy of the metric, as it may be too vague. It's valid only for California and may not reflect the difficulty of the chosen driving environment. Nonetheless, it's pretty much the only metric that's relatively objective and can be used as a metric for comparing the AD technology from different companies. This figure from 2019 shows that Waymo has the highest autonomous miles driven per disengagement, which is 11.1 miles. And the Cruise Automation, which is, I think is a spin-off from GM, has 5.2 miles. Zoox has 1.9, Neural has 1.0, and Pony.ai has 1.0. So these are all startup companies working in the space. So when will AVs arrive? So this figure from Newtonomy, I think. So it says that this prediction was made from 2017. So it predicts that the level 4 and 5 AV penetration will gradually increase until the 2040, when 75% of all vehicles are autonomous, and 2050 when traffic fatalities will be reduced by 90%. And so the green vehicle is for mobility fleets, such as fleets owned by Uber. The red curve shows the personally owned vehicles, which should be slower in adoption because the mobility fleets, the companies are financially motivated to adopt the autonomous technology, whereas individual owners may not be as motivated. But in any case, the prediction is around 2040 to have high penetration of AVs. But many people have made many different predictions. So Edwin Olsen, CEO of May Mobility, says, drew an analogy between the Moore's law in the semiconductor industry and the miles between disengagements in the AD industry. So the Moore's law says that the number of transistors on the chip doubles approximately every 18 months. It's not a real law. It's kind of an observation of the trend that's happening in the past many years. So this is exponential growth rate. So if we had a Moore's law for AD, for example, the number of miles between disengagements will double approximately every 16 months. If you had such a law, by interpolation from human performance, which is 10 to the 8th miles per fatality, and best reported self-driving car performance, which is 10 to the 4th miles per disengagement, and then we'll reach human level performance in 2035. So obviously, this is assuming exponential growth, which is the best case. Chris Ormson, co-founder and CEO of Aurora, has made many predictions in the past years. From 2009 in 5 years, 2012 says in 5 years, and 2015, 2018, he always says in 5 years. But it hasn't arrived at least this year. So here are a few high-profile AD accidents. So this accident happened in 2016. The Tesla Model S Level 2 autonomous driving vehicle was driving at 74 miles per hour on the highway when it was struck by a semi-truck. So the driver's hands were off the steering wheel for a total of 37 minutes. That is, autopilot was engaged, and despite repeated visual warnings. So what happened was that the Tesla vehicle was going in this direction, and there's a large white truck turning left in this direction, and it just ran into it. So Tesla says neither autopilot nor the driver noticed the white side of this tractor trailer against a bright lit sky. So the brake was not applied. So it mistook the side of the truck as part of the sky. So obviously, it's a failure of the computer vision algorithm for object detection. Maybe a LiDAR could have prevented the accident, but Tesla cars don't have LiDAR. So Tesla used to use Mobileye's hardware platform IQ for their vehicles. Mobileye is a subsidiary of Intel located in Israel. They make smart cameras that perform object detection and recognition very well for autonomous driving. But after the accident, they broke up, and Tesla started to develop its own hardware platform called FSD, full something driving. I forgot the acronym. So in 2018, a man died from a high-speed crash because his Tesla autopilot system steered the system into a median on Highway 101 in Mountain View, California. So here's the highway. So this is the lane, and the vehicle steered to the left and onto the median, causing a crash. So the National Transportation Safety Board investigation report lists 23 findings that enumerate all the factors that contributed to the fatal collision. So the limitations in Tesla's autopilot lane keeping assistance function caused the vehicle to veer into the median and failed to provide an alert to the driver in the seconds leading to the crash. So in the previous accident, at least the vehicle alerted the driver, but the driver did not take control. In this case, the autopilot did not even warn the driver. So essentially, the lane detection function failed. So it thought that the lane leads this way, but it actually leads into the median. So the collision avoidance system was not designed to detect a crash attenuator. A crash attenuator is this highway thing here that's designed to alleviate, attenuate the impact of the crash. So this particular thing perhaps was not in the training set. Perhaps it was not well represented in the training set. So Tesla's vision system did not detect it. So it thought it looks like a lane. If you look at it from a far away, the arrows kind of look like a lane directions. So this resulted in a severe crash in which the automatic braking and collision warning system failed to activate. And also the driver was not paying attention. He was likely playing a video game at the time. So it's a failure of the computer vision algorithm for lane tracking. So this is the after the accident picture with the white foams are the firefighters' fire extinguisher foams. So even in 2020, Tesla still cannot recognize white trucks. So this is news in June of 2020. Tesla on autopilot crashes into overturned truck on busy highway in Taiwan. So you can see the footage. See, it's coming this way. It just did not see it at all. It just crashes right into it. So in all these accidents, Tesla really has no responsibility, because in the user's manual, it's clearly written that it's a L2 vehicle, and human is responsible for the safety of the vehicle, and a human should take over control whenever there's a warning or whenever something is unsafe. So if a driver overtrusts the technology and the vehicle has an accident, legally, Tesla is not responsible for it. So here's the 2018 accident of that killed a pedestrian by an Uber vehicle. So here's the footage from the front camera of the vehicle. So a person with a bicycle walks out of the darkness and was hit by the vehicle. Here's the reaction of the safety driver. Yeah, he was not paying attention at all. The safety driver is supposed to be always attentive and alert, and take emergency measures whenever he sees something dangerous. But this particular operator was not paying attention. So, but on the other hand, it is very dark. And the pedestrian was crossing a highway, kind of a highway. So on this, the vehicle was driving normally on this road, and the pedestrian is not supposed to cross here, but she crossed, and the hit was hit by the vehicle. So this AV is level 3 or 4. It was equipped with both LiDAR and radar. So after the woman was detected on the road 6 seconds before impact, the system, the later investigation revealed that the system first classified it as an unknown object, then misclassified it as a vehicle, then a bicycle. Well, it is a human with a bicycle, so the bicycle is perhaps okay. But 1.3 seconds before the Volvo system, the default system that comes with the Volvo car tried to do emergency braking maneuver, but Uber had disabled it for A/B testing. So they replaced the default Volvo control system with their own AD system. And on the other hand, the safety driver was not watching the road moments before the vehicle struck her. But as you can see from the video footage, it was probably too dark for the human to see her in time anyway. But experts have argued that the LiDAR should be able to detect this woman. because LiDAR is not affected by lighting, but it did not detect it. So here's the AD landscape today. It's a very hot area. So you have autonomous driving systems such as Uber, Cruise, Drive.ai, Waymo, and others. And you have suppliers that provide data and simulation, light detection and ranging LiDAR companies. And you have companies that provide V2X connected car communication services. And you have companies that provide apps and mobile infrastructure. And for mapping, for providing high definition maps, and many companies in this space. So someone said there was a Tesla accident in 2021, which is similar to the 2020. It may very well likely to be. Yeah, I see one Tesla vehicle struck a police car in March, just last week. Yeah, so it may very well be because Tesla has so many vehicles on the road. It has a higher probability of getting into an accident as long as there's no fatality. It typically doesn't make front page news. It's when someone dies and then people pay attention to the news. So let's move to the next segment on the overview. So the AD processing pipeline. So the four major tasks of an AV, first is localization. That is to answer the question, where am I? Next is detection, so what's around me? And then is the prediction, where are they going? And finally, planning and control, so where should I go? So as you can see, gradually you're adding more and more information to your with your sensors. Initially, you can only localize yourself here, and then you detect the stuff around you. Could be pedestrians, could be other vehicles, and then you try to predict the trajectories of the surrounding vehicles. So this one is going straight, this one is turning left, and so on. And then finally you make a plan to go forward. So the AV processing pipeline can be divided into roughly 3 stages. The first is sensing. So you have different sensors with possible high definition maps available or not. And the perception, the sensing part, tries to understand the surrounding environment, including localization, detection, and prediction. And then after you have done that, you go into the planning stage. That is a decision making in the context of other road users. And finally, you have the acting stage. That is, you try to control the car's throttle and brake and steering wheel to move the car according to the planned trajectory. So the environment perception, you take from the various information from various sensors, including LiDAR, cameras, radar, to perform dynamic object detection and tracking of the objects and object motion prediction to predict the dynamic motion of the objects. From the GPS or IMU and wheel odometry sensors, you perform localization to return the ego vehicle's position. And from high definition roadmap, you can detect the static objects. So the HD maps are optional. So that's the first perception stage. The output is the vehicle's ego vehicle position and the static and dynamic objects around the ego vehicle. So prediction is a very difficult problem. So it's based on state information. So the example you can see here that the vehicle is going from lane 0 to lane 1 to lane 3 and lane 7. So each one is a segment in the map. So you're trying to predict this vehicle's trajectory to be this one. So you can do this with a classification-based method. A very hard pedestrian motion is very hard to predict. So it's a very active research topic. Pedestrians are not like vehicles because pedestrians can move and turn at any time to any direction. So you can predict based on the pose and other visual cues. In general, it's a very hard problem. For example, if you see two people on the curb talking to each other, then it's very likely that they'll stay there. They won't go walk into the road. But if you see someone waving to someone else on the other side of the road, then it's very likely that he will move across the road. So you must infer the human's motion from visual cues like that. From a computer vision perspective, it's a very high-level semantic information and very difficult to predict. So environmental maps. So this is, you have different types of maps, from occupancy grid map to localization map to a detailed road map at different levels of granularity. So for motion planning, you have different levels of planning. So at the highest level, you have Mission Planner. That is given a roadmap, you try to plan a path from point A to point B, say from your office to your home. And in the middle is the behavior planner. That is, you choose the behavior to go forward or stop or turn around and so on. And finally, at the lowest level, you have the local planner. That is, given that you want to turn to the left at the intersection, plan a detailed path and the trajectory, the speed along the path to make the turn without hitting the other vehicles and pedestrians. So here's the emission planner. So you want to go from point 0 to point 1, and you have this map with the cost on each edge of the graph. The cost could be the distance or could be the travel time, depending on the time of day and other factors. So the job of the emission planner is to find the shortest path along the graph. The behavior planner plans the set of high-level driving actions or maneuvers to safely achieve the driving mission under various driving conditions. Stop, track speed of the preceding vehicle, follow the leader, and decelerate and stop, and so on. The local planner plans a safe and smooth trajectory. Trajectory is a vehicle pose as function of time. So, so a path is a particular line, particular, say this is a path, and trajectory is the path plus, it's the path as a function of time. So it adds speed and acceleration information. So it's important to consider the time factor because it affects the occupant's comfort level. So if you're always braking and accelerating, it's not very comfortable to the occupant. And also it affects the safety of the trajectory. So a particular trajectory may be safe or unsafe depending on its speed along the trajectory, as well as the other vehicle speed. So in this case, this vehicle is planning a trajectory to perform a lane change maneuver. So there are all these different possible trajectories, and the planner needs to pick one that is safe and efficient and comfortable. So the controller, there are essentially longitudinal speed control and the lateral steering control. So the steering controller outputs a steering angle, and velocity controller outputs a throttle percentage and brake percentage. So the most common control algorithms are PID, proportional integral derivative control, and MPC, model predictive control. We'll discuss more details later in the course. So the planner feeds the planned trajectory, that is a vehicle pose as a function of time into the controller, and the controller's job is to follow the planned trajectory. So the classic AD processing pipeline has separate algorithms for each processing stage, including perception, planning, and control. So where does machine learning and deep learning come in? So convolutional neural networks for perception is well accepted today. So essentially, you are placing a deep neural network as a perception algorithm to replace the more traditional computer vision algorithms. So that's actually the current industry practice. And DNN trained with imitation learning or reinforcement learning for the decision-making part of the pipeline is still in the early research stage. So it's essentially you are letting the neural network cover more of the processing pipeline. It could be halfway, could be performing perception and planning, but leaving control to the traditional PID controller, or could be end-to-end, from perception to control. Entire pipeline is replaced by a single deep neural network. So halfway hybrid approaches also possible, where you map from input image pixels to waypoints used for planning, and then subsequently the planner and controller is done by classic techniques. Even though the IR and IR-based approaches are still immature, several companies are betting on it, including Waymo, Voyage, and Wavy, and a few others. So this introduction, PowerPoint has a few sections. I have next section is sensors and perception. I'll discuss the various AV sensors, camera, LiDAR, and radar, and HD maps, a few slides, and then hardware platforms, software platforms, and ethical issues, and finally V2X communication. So I think I'll stop here today. So any questions on the lecture material?
Yeah, I have two questions.
Oh, sure.
So the deep learning, you said the single model which replaced the traditional approach, right? Classic pipeline. And here it's like multiple models are combined to each other, right? So.
Yeah. So the traditional pipeline, has its so-called modular architecture, where every block here is a separate algorithm.
Yeah.
When you apply deep learning, you can either still keep the modular architecture and replace a single module, typically the perception module, with the deep learning, but leave the others to the classic modular architecture. Or you can replace part of the planning also with deep learning, or you can even replace everything with deep learning. So it depends on how aggressive you are in applying deep learning.
Yeah, I mean, in that case, if it's a single deep learning model, the learning error, this gradient descent, error correction mechanism, do you think it's gonna be very tricky to fix something if something wrong happens in one of the middle models?
Yes, that's the main critique, the main criticism against this kind of end-to-end approach. So let me flip to a later lecture where I introduce the different approaches. So the earliest end-to-end approach is the very old 1990 vehicle from CMU. So it mapped from the input camera image going through a neural network to control a vehicle, but it's a small-sized vehicle driving on a road by itself. So it's very simple. And 2003, Yang LeCun, the inventor of convolutional neural networks, had this vehicle Dave, which also maps from image to decision. And the modern version is the NVIDIA Net from 26. Polynet is also called NVIDIA Net, I think. So it is trained by collecting data on an actual vehicle and using imitation learning to imitate the human driver's actions. And the mapping is end to end, from sensor to throttle and steering.
So that includes the controller part too.
Yes, it directly outputs the steering.
Okay.
So here's the Polynet driving demo. So essentially, here's the camera image. So it actually views every single frame as a static picture and maps from the picture into a steering angle.
Wow. Okay.
So, I mean, it is, you know, at a research stage, there are a few other attempts later, and there are a few tricks. For example, they have 3 cameras, center, left, and right. So the left camera collects images that's kind of leaning on the left. So you should associate a turning right action to the left camera image. So it's kind of a way of enhancing the training set, adding more data to the training set. And later, Waymo had another system for the end-to-end approach. No, Waymo's system is a kind of mid-to-mid. That is, they have this perception module providing a bird's eye view, and then they have the machine learning model is mapping from the bird's eye view to a planning output, planned trajectory, and then the controller is the traditional controller. So there are many different variants. You can replace some parts of the end-to-end, some part of the driving pipeline, either end-to-end or the perception or the planning. So there are workshops dedicated to applying the reinforcement learning to autonomous driving every year. So it's a very active research topic. But as far as the vehicles in deployment, for example, Tesla, I think they only use deep learning for vision, for perception only. And the other auto OEMs in Detroit, I think they heavily rely on the classic methods. But some startups are more aggressive in applying reinforcement learning and imitation learning to the end-to-end approach.
So one more question was that when you have the PID controller, which controls the steering wheel, and there is, in the feedback loop, you found out the direction is not completely correct, and then through GPS or localization, you found it. How does this correction process works from end to end?
So the PID controller is trying to track a trajectory output from the planner. And if it detects an error in localization, maybe, and you can correct it. But for end-to-end approach, I'm not exactly sure what you mean by correcting an error. But in general, yeah, go ahead.
Yeah, sorry. So steering wheel, it's just specifying the angle, right? So actually, maybe it's not exactly doing precisely following that angle. So there is still some deviation. But through after the vehicle is moved, let's say 1 more kilometer, and then he found, okay, there is slight misadjustment in this.
Well, for the end-to-end approach, for example, if you are controlling the steering wheel and driving, and you find out that the camera image shows that it's hitting the curb, then it'll correct, right? It'll turn right. So
Yeah.
it has some kind of correction capability.
Okay.
Yeah. But
Okay.
in general, the end-to-end approach is viewed as not very reliable because deep learning is well known to be a black box system, and it lacks robustness and explainability. So sometimes it may make very strange decisions, that's not explainable. So many people are working on different techniques. For example, researchers have developed explanation systems for deep learning. So for example, if you're going through the intersection or turning right, it'll provide a textual description of why you're doing it, the car is doing it. It may say, okay, there's a pedestrian on the left and he's crossing the road, so I must avoid him, kind of a text shown to the driver. So that kind of system is pretty much in research. In general, for deep learning in autonomous driving, the only way to make it more reliable is to do extensive testing in different scenarios. And even so, you cannot make very hard guarantees to its performance, like the classic techniques.
Yeah, for unseen data also, it may not perform well, right?
Yeah, unseen data is the main challenge to application of deep learning. For example, the side of the truck. Tesla vehicles have seen many trucks on the road, but in the training set, maybe there's none or a few pictures of a truck turned on its side, right? So it has rarely seen this kind of thing before. That's why it could not recognize it. And also this particular crash attenuator, this particular image perhaps is not well represented in the training set.
Yeah, got it. Thank you very much.
Yeah. Please read more about them as classic pipeline model. You can search about the nice. If you read recommended references instead of searching. Yeah, so in the many of the slides have in the very bottom, I have a link. For example, this picture comes from this article, and some of them I don't have. So this picture is from this blog. This is from the news. Yeah, and I often put a page at the end of every lecture, for example, as additional readings. So this particular report is a very good overview of the state-of-the-art technology in 2020. So the particular thing you asked about, the classic techniques, yeah, I think I can pull up a few links.
That would be nice. Thank you very much.
Yes, I will do that later. Okay. So Samuel says, what is the current state of the art in AV driving? Is the future trajectory pointing towards deep learning, reinforcement learning, or a more modular approach with deep learning plus classic AI? I mean, it's hard to say. The classic, the classic methods are not really AI. They are like PID control and A-star planning and the traditional planning methods. So I think at least in the near future, I think it'll be a combination. The end-to-end approach, like Polynet from NVIDIA and ChauffeurNet from Waymo, they are pretty recent publications. If you recall from that PowerPoint I showed you, ChauffeurNet from Waymo was from 2018, and Polynet was from 2016. So I would say it's still in the research stage, and with enough data and very good training algorithms, I think they have very good potential. But if you look at maybe in the 5-year horizon, I think the dominant paradigm, it will still be a combination of perception with deep learning plus classic planning and control algorithms. Samuel says, DeepMind's current state-of-the-art are increasingly more pure end-to-end deep learning based and less hybrid with additional classic algorithms. Well, DeepMind is working on reinforcement learning mainly for video games. So they are very good at starting from the Atari games to the AlphaGo for playing Go to AlphaZero, that is one agent that plays Go and chess and a few other games. They have done they have reached the top level in terms of video games, but they don't work on autonomous driving, so it's not part of their business. So I think it's not a good analogy. They showed that RL can be very powerful for games, but the real world is very messy. So even for complex, difficult games like Go, the search space is huge. It's very large, but it's the entire game's board state is visible, so it's a full information game. Well, they have later been working on partial information games like playing cards, but it's still part of the game domain. But for autonomous driving, the real world scenarios can be so diverse, so complex. Like, you know, they overturned a truck on the side, like different weather conditions, like erratic pedestrians. So there are so many corner cases that it's difficult to represent everything well in the training set. So people have devised many tricks, like enhancing the data set with some rare objects that's not really seen in real life, or devising scenarios, self-driving car driving scenarios that's in the simulator that's rarely encountered on the road, to try to represent more of the corner cases. But it's still very difficult. So there are lessons learned. So AlphaGo these kind of games are very useful for advancing the IR algorithms. And the advancements gained from the video games can obviously, and also the Go games can obviously be useful for other tasks. But for autonomous driving, I think it's a much more difficult problem than playing games. Okay, are there any other questions? I think we're already a little bit over time. Okay, so then we'll finish today, and I will see you on Monday.
Thank you.
Okay, thanks to all. Goodbye.
Bye.
Thanks.